Let's start. So welcome the team for this session on barrier instructions. Probably the team here attendees is aware of barrier instructions or not, I'm not sure. Though this is not transparent to the users, like barrier instructions can be included in your program. It's part of assembly, but in ARM compiler, they have given them to be used as an intrinsic functions. You can call this instructions, assembly instructions in your C program as a intrinsic functions. Okay, so I welcome you all for this webinar on barrier instructions.
Geeta, could you come a bit closer to microphone because your voice is a bit feeble for me at least.
Okay, fine. So
Yes, it is the same with me.
Yourself mute to avoid any crosstalk, and questions you can put it on the chat window if at all you have any Q&A. Well, yeah, I'll come near to the mic. So hope the team is able to see my screen. So coming to barrier instructions. So barrier is so before we come to barrier, we have to understand what is memory model. So here the team might have worked not only on the ARM but also for a different processor core device, and you might have come across memory model in all the embedded processors. So memory model, sorry, it's basically on how the memory map is being divided between flash, RAM, peripherals, whatever the on-chip resources, how it is being divided. So why we are talking about barrier instructions and why memory model is coming into picture. ARM architecture has a very weak ordering model. Okay, so what does that mean? It has weak memory model in the sense any access we do to the memory. As you know, ARM is a load store architecture. So we processor cannot directly
చెప్పుకోవాల్సినంత అవసరం అది నేను చెప్పుకోవాలి కానీ ఇంటికెళ్ళి మమ్మీ భలే చేశారు
Rajkumar, please mute yourself. Please guys, please follow the webinar ethics. Thank you. So ARM architecture follows a weak memory model. So weak in the sense, here you know ARM is a load store architecture. ARM cannot directly so it works on load or store architecture. It cannot directly operate on the contents of the memory. The memory contents has to be brought to the register. We have to modify, and then the modified data is written back to memory. It is read, write, modify, or read, modify, write. Okay, so here any LDR STR instructions can be repeated in any order. It can execute for normal memory region. So what is normal memory region? So before that, ARM gives actually three types of memory region: normal, device memory, and strongly ordered memory. So normal memory region is usually the memory which is for the flash memory or the program memory, RAM, on-chip RAM, or even off-chip RAM. Okay, so these are configured as normal memory regions because processor can perform any number of load and store instructions. They can repeat it how many times it's required. It can be executed in order. It can be executed out of the order. But these memory regions are treated as normal. Whereas device memory access, specifically each of the peripherals of the specific processor microcontroller will have a dedicated memory allocated to it. So if processor is accessing those memory locations for the peripherals, especially to update any peripheral registers and all, it has to be device memory access. It has to be configured as device memory model. And here you cannot do the repeated, uh, you cannot execute LDR STR many times, you cannot repeat it. Only once it is executed, is executed. You cannot do multiple times of LDR STR access to the device memory access. Another is strongly ordered. Strongly ordered is specifically for the memory region where all the control registers are stored. Usually the registers associated with controlling the operation of the processor or an MPU, all the registers where they are stored. So strongly ordered is used for that memory region. So let's talk about normal memory region. As I already said, processor can do any number of LDR instructions. It can repeat it many times, but ARM also allows speculative access. So whatever the LDR STR access the processor performs to these normal memory regions might not execute in the same order as you have written in the program. So in program you have written LDR STR in some flow. You cannot expect the processor will execute all these instructions in order. So only it is called weak memory model. Weak ordering model. Normal memory regions are always weakly ordered. Weakly ordered means the code will not be executed by the processor. May not be, it's not compulsorily, but in some scenarios, it may not execute the code in the order. Why? Because ARM architecture allows something called a speculative access. So in architecture only it is hard coded that the processor can easily go and fetch the memory speculatively, means though there is no explicit access also, no explicit reference also, but still the processor can go and access that specific memory location. So examples of such speculative access is we have branch prediction, out of order data load, speculative cache line fills. Okay. So even though when the cache line fills, please remember this I'm talking to for all the ARM architectures in specific to Cortex A, R, and M. Okay. So you may not require barrier instructions because M is a very simple microcontroller processor where it's very architecture is simple. There is no co-processors involved, so there is no superscalar pipeline where you have 9-stage pipeline, 11-stage pipeline, 13-stage pipeline. No, it's just 3-stage pipeline, and it is a very well defined and a simple processor. But this is applicable for Cortex A and R, which has a superscalar pipeline. So speculative access means even though the processor has not access any address or data, the architecture will go and fetch the data. Okay, so even though processor has not requested any data from the cache, the cache will be filled with the memory from data from the RAM, on-chip RAM or off-chip RAM. So in such cases, for such scenarios, it uses the speculative accesses. So please note speculative access only works for normal memory. So that means speculative access works for the memory model which are defined as normal, which is flash, RAM, on-chip RAM, off-chip RAM. Speculative instruction fetches are not allowed to any region marked as execute never except when we are defining suppose if I take an example of a Cortex A or a Cortex M which has a 4 GB memory address space, I can tell to the a linker that this specific web block has to be used as flash or a RAM. And I'll also give what are the access attributes for those blocks, whether it is read only, write only, execute never, it is cached, non-cached. In cache means it is what are the different types of cache properties or whatever it follows. All those I have option when I'm defining a memory model. Okay. So if the particular region is marked as XN, execute never, then that's if at all architecture go and fetches from that location speculative access, the result is unpredictable. Okay, so why do I care about access order? For me as a program, I'll write a program, I'll write all LDR STR instructions, I write program in my ID or whatever, if it is compiler or if it is assembler, I need not bother about the order. But in some scenarios order has to be taken care. Where, what are those scenarios? When it is a multi-core environment where you have heterogeneous processor, or you are operating on an SoC which has more than 4 or 6 or 8 cores. You're sharing the data between the different CPUs. Or different tasks or threads. Example through mailboxes or sharing data with the peripherals. So that is through DMA. So data memory access will directly DMA is a peripheral which will directly access the or modify the memory without the intervention of the processor. Next, modifying the instruction memory. So in any case, you have to, because ARM processor gives us the option of loading the code to the flash or loading the code to the RAM. So you can execute the code either from flash or from the RAM. In some cases, I want the processor to execute the code from the RAM instead of the flash. Then we are actually modifying the instruction memory. So we have to tell to the processor that you have to execute the code from the RAM, not from the flash. This when it happens when I'm loading the code to the RAM, and I have to also locate the vector table, intervector table or exception vector table. So vector table register has to be written. Then only processor will, if any exceptions or interrupts come, processor will go and execute, get the address of the exception or interrupt from the vector table. Or memory management scheme. We can also, some processors also come with memory protection unit feature, where we can define the entire memory region as we require as per our requirement. In the above scenarios, to ensure whatever the LDR, SDR instructions I have written in my program executes in the order by the processor, we need the barrier instructions. Okay. Compiler or assembler. Suppose I'm talking about here is ARM compiler, because we are the authorized and prime distributors for ARM software solutions in India. I'm from GSAS MSPL. So this will not include any automatically barriers for you. You have to include depending on the program requirement. So what are those barrier instructions? So these barrier instructions will ensure that the code is executed in order. We have DMB, we have DSP, we have ISP. DMB is data memory barrier, DSP is data synchronization barrier, ISP is instruction synchronization barrier. Okay. So in this presentation or in this webinar, I'll be giving you just a brief introduction about what are these barriers, where are the scenarios you can use them, and how you can use them. Though all the examples are in assembly, but you can also use this as an intrinsic functions in your C program. So coming to data memory barrier, conversion versus to data synchronization barrier. So both are for data memory only, but there are some differences between DMB and DSP. DMB is very less restrictive than DSP. Okay. So what will DMB do? It only ensures that if processor is performing any explicit data accesses. Okay, LDR and SDR is done to the cache memory, or instructions associated with accessing the memory related to the cache. Then only this DMB will ensure that whatever LDR instructions the processor we have written in the code for accessing the cache to read in or to update, it will ensure that it execute in the order. Okay. So before DMB, any explicit accesses related to cache will be observed, in the sense will be ensured that processor will execute them at any cost before any such instructions appear after DMB. Okay. In case of DSB, DSB is very strict and stringent. So only we have to be very smart in using this DSP instruction in our program. So DSP sees that, we were talking about barrier instructions for all LDR and STR accesses, but DSP also ensures that any instructions before DSP has to be executed. It can be arithmetic operation related instruction, it can be an exception, it can be any memory accesses, explicit memory accesses, it can be anything. It ensures that all those are being executed and completed by the processor before any instructions which appears after DSP. So all cache branch predictor, TLB maintenance operations. I'll tell you what is TLB and all. If the team is aware, please bear with me. It's just, it could be a repetition for you, but this benefit for the others who doesn't know the TLB or for whom it may feel it is weak and Latin, but I'm sure TLB is a very common word. So let's see now how to use the scenario of DMB. Okay, so here okay, so this is just an example. So here you can see LDR R0 R1. So this instruction means first instruction LDR will load the contents of the memory pointed to by the register R1 to R0. So DMB instructions ensures that this reading of the data from the memory completes successfully. Memory in the sense here I'm reading the data from the memory to the cache, it can be because it's explicit access. Okay, then add R2 #1 whatever, and then we are storing some data to R4. Okay, so this DM instructions ensures that this store happens only after reading the data from the cache memory. So this add instruction can be executed speculatively, means we cannot tell processor that add has to be executed after DMB. It can execute even before DMB also. So only I told DMB is very less restrictive, because DMB only observes and ensures that any explicit memory accesses are executed or completed before any such instructions come after DMB. But it has no control on arithmetic related operations like add, multiply, whatever it is. Now add R2, #1, we have no way to tell to the processor that it has to be executed after DMB. Due to speculative fetching, the processor can still execute add R2, #1. But this DMB will ensure that store happens only when the LDR is completed. Okay. So next, specific to data or cache maintenance operations. Suppose here first line DCC SW data cache clean. Then effect of data cache clean might not be seen by this instruction. So after cleaning this data, cleaning the data which is there in the data cache, then we are loading the first whatever the cache data was there, we are cleaning it, and then the data is loaded from the memory to the cache. So DMB will ensure that this loading of the data to the data cache is executed, and later on we can also, if you want, we can load the next memory to the other memory contents in the register. So DMB is just for explicit memory accesses. It has no control on the ALU operations or arithmetic operations. On the other hand, DSP is a very strict barrier instruction. So in the previous example, if you take, so this is DSP ensures that the storing of the data has been completed. Whatever data you want to write it to the memory has been completed. Okay, so even the add instruction will not execute until the storing of the data is completed. So DSP also controls your arithmetic operations, but DMB doesn't do that. Doesn't mean DSP will not control memory accesses. DSP ensures any instructions before DSP instruction are executed by the processor. Okay, maybe now or out of order, whatever, but it ensures that all the instructions are executed after, even before any instruction which appears after DSP. So now let's see an example of mailbox. So in the mailbox we have P0 flag. So this mailbox is actually, you can take it as two processors. You can take as a co-processor or a thread or whatever. P0 is writing a data to the mailbox and it sets the flag to the other thread saying that I have put the data in the mailbox, please read it. So P0 has to here, R1 will point to the data which you are loading to the mailbox and R2 will hold the flag to indicate whether the mailbox is full or not. So R1. So R1 is the data. So we are R5 is whatever the data I want to load it to the mailbox. That has the data which has been loaded to the memory which is pointed to by the R1. So str R5 we load the data to the memory box. Then the DMB comes. So DMB, because it's a memory access instruction, so DMB will ensure that the data is at any cost returned to the mailbox. Whether it's the mailbox is loaded with the data. After that only, it will set the flag saying that the mailbox is full. So, in other words, the mailbox full flag will not be returned until the data is loaded to the mailbox. That is what DMB ensures. Next P1, what it does, it will check in what next what it has to do is it has to check whether the full that flag is been set by the P0. So that flag indicates to the P1 that yeah, there is a data available on the mailbox. And once that flag is set only, the P1 will be able to read the data from the mailbox. Okay. So here also in this case, first we'll wait for the flag. So we are reading the flag which is pointed to by the address R2. We're loading it to some register and we are comparing with 0. Comparing with 0 indicates whether that memory location is 0 or not. 0 indicates there is a data available. So means 0 indicates the flag is being set. Means that the memory box is full. Once, only after getting that flag set, then only P1 will go ahead and read the data from the mailbox. So this DMB ensures that the data is made available in the mailbox. After that only this LDR instruction executes. Next, speculative access across barriers. So here we are talking about P0. Just a second. Sorry, there was some call. Okay. So now access across barriers. So we have P0 cache processor and P1 is the bus master. We can take it as a DMA. Okay. So here we are first using DCI MVAC, which is to we are whatever the memory address which the DMA will be writing, we are just invalidating it. Means if anything is there, data in the data cache has been cleared. Then we are giving DMB to ensure that the cache maintenance operation is clear. The specific memory address is been, the cache is cleared. Then we are setting the flag to the event saying that that memory address to which DMA has to write is been available for, it's been cleared and it is available for writing. It's been kept empty. Okay, so once after that, it will check for wait for R4 is equal to 1. R4 is what? That is a flag set by the DMA engine. The DMA engine ensures that the flag by the P0 is set, indicating that the memory is free or kept empty. Then it will write the data. STR is for writing the data. And then DMB again to ensure that the data is written by the DMA engine to the specific address. And it sets the flag also to indicate to the cached processor saying that the data has been written to the DMA and the processor can read the data. So the first wait in the P0 will ensure that DMA engine has written the data to the memory. And then it reads the data from the memory, which is pointed to by the R1 here, whatever that address. Okay. So here we have used DMB because though we have invalidated that particular region of memory, which is the data, that specific entry in the cache, that specific memory has to be written to. Sometimes even before the processor comes to the, even this DMA engine, before the DMA writes to that specific memory, processor may speculatively fetch and fill some random data to the memory. So only this DMB will ensure that this has been invalidated, or if there are any dirty lines or dirty fields. So hope the team knows what is dirty. Dirty means processor has done some operation, it has updated the cache, but the architecture has not updated that, copied that updated data to the memory. Those are called dirty cache lines. For such memory, there is a dirty bit also set by the architecture. So any such things are there also, it will be cleared. That is why we use invalidated region, and DMB will ensure that it is executed. So same thing is explained here in theory. Okay. Now we will come to instruction barriers. So instruction barriers is instruction synchronization barrier. So ARM architecture defines the context as a system setting in CP15. So please note I'm talking about Cortex A. Cortex A as, I believe, 15 or 16 coprocessors, CP0 to CP15. And any change in the context happens. Context in the sense execution mode changes, or if the processor has to take a switch, branch, anything, then that related information is stored in CP51. What are such context changing operations? It can be cache or TLB or branch, sorry, cache, TLB or branch predictor maintenance operations. So TLB is nothing but translation look aside buffer. So what is this TLB? Basically, this is used in the processor which has MMU, memory management unit. So which is there in Cortex A. So what is this memory management unit does is, with the help of MMU, processor thinks it executes that all the functions individually, saying that they are not dependent on other functions. It executes its own virtual memory space. Virtual in the sense that memory is not ready, not available in the processor. So what this TLB does is, it has an entry for each of the virtual address. It maps to the physical address. Physical address is the actual address which is present on the target board or on the device. So TLB is translation look aside buffer. So whenever processor fetches a specific virtual address, it will look at this TLB and it will find out which is the corresponding physical memory mapped to it, and then it executes. This is how the Linux application executes, because Linux application always executes in virtual space only. It's not the physical space. Okay. So any cache related operations, TLB, branch predictor, that can be written as a context changing, or a changing to system control register, translation table, or context idea. There is a bit in the CP15. So any such context changing operation has to be ensured to the processor that it has to be executed completely before it switches. So what are those context synchronization events? Even before such events happen, we have to ensure that processor executes, or it takes care of everything before it jumps or before it changes the context. For example, taking an exception. So before taking an exception, what the architecture, which is hardwired architecture in ARM, does is, it pushes all the registers onto the stack, and it gets the address of the exception handler from the vector table. So this is the hard-coded thing which is implemented in the architecture itself. So that the processor has to ensure that it pushes all the registers on the stack, which is it has to save the context of the stack, and then it has to go and fetch the instructions from the exception handler. Or it can be during a returning from exception. So before returning from the exception, this one registers which are pushed onto the stack has to be popped up, and PC has to be read so that it returns back to the main flow from where it interrupted. Or in ARM, it also checks if there is any pending interrupt before switching to the main. If there is any pending interrupt which is a high priority interrupt than the current interrupt or exception, the processor will quickly jump to that exception or interrupt and execute it. Then it comes to main. Next is instruction synchronization barrier. So all these three, taking an exception, returning from an exception, or an instruction synchronization barrier, are treated as a context synchronization event. When any of these event happens only, it shifts the process will shift the context, or it can be due to any of the maintenance operations which we talked about in the context changing. So what does the ISP does? ISP stands for instruction synchronization barrier. It flushes the pipeline. Okay, because due to speculative access processor, there will be a lot of other instructions which have been fetched to the pipeline, which have been already decoded, read, whatever, executed. So those instructions will be flushed from the pipeline, and processor has to fetch from the new address as per whatever. Suppose if you take exception or whatever it is, it will start loading the code from that specific address. Okay. So this ISP ensures that all the context changing operations are being completed before the processor starts executing from the new context. Like I told in taking an exception, it has to push the registers onto the stack. So ISP instruction will ensure that processor will do all those completely, and then only the processor can switch to the new address for the exception handler or ISR handler. Okay, so let's see an example of CP15. So CP15 here is, for example, CP15 is a control register we can take, or a coprocessor 15, to enable the FPU, floating point unit, or a neon unit. So you need to first enable the access to coprocessor 10 and coprocessor 11. Okay, how do you enable this? We write it to a coprocessor access control register, which is CACR. Okay, this is an example I'm giving for Cortex A. Okay, you can also map this to any of the other architecture where it is coprocessor involved, but as far as my knowledge, only Cortex A is the one which has coprocessors. Cortex R doesn't have coprocessors, but there we have cache memories, tightly coupled memories. Okay, so here MRC and MCR. MRC is a dedicated instruction given by the ARM to suppose as I told, ARM cannot directly write to a memory. So it has to read the contents of the memory to a register. So MRC, so CACR, that is the address of a register. So we cannot access we have to first load the contents of the address to register R1, then modify, that is set the whatever the required bits for accessing the FP or neon, and then write the modified data to CACR to ensure that the FP and neon are being enabled. So in this case, ISP is required. If ISP is not there, due to speculative fetch, due to speculative access feature, processor may go and fetch this VMSR instruction. So this VMSR instruction will turn out to be invalid instruction or undefined instruction, because processor doesn't understand that instruction. Because this particular instruction is understood only by the coprocessor 10 and coprocessor 11. Okay, it is not understood by the normal ARM processor. So this ISP ensures that CACR is written completely, CACR is enabled completely, and then if processor fetches this VMSR, it will be able to execute it, because it understands these instructions are associated to CP10 and CP11. Okay, so In Cortex, you know how the co-processors work. Every instruction processor fetches all the 15 co-processor also fetch those instructions. Okay, and every time when it decodes that, each co-processor decodes the instruction. If that particular instruction is for that particular co-processor, then that co-processor will execute that instruction. Processor will not execute that. So it's a very complicated architecture, very complex architecture in Cortex-A. So this ISB is very much needed to ensure that CSCR is completely enabled, completely written, and FPU and FPU or Neon is completely enabled. So VMSR instructions executed by the processor without any issue. Otherwise, it will be treated as a undefined instruction because ARM processor doesn't understand what is VMSR, but CP10 and CP11 co-processor understand what is VMSR. So until you don't enable that co-processors, it will not execute at all. So ISV is required. Showing you the scenarios where these barrier instructions can be used, but if you go to developerarm.com, you will get a lot of information on barrier instructions on how to use various scenarios. Not all the scenarios require, but some scenarios like this, you need a barrier instructions. Okay. Translation table change example. So as I told, TLB, translation Lucas site buffer, that actually keeps the virtual memory to physical memory mappings. Okay. So in this case, you can see we have used DSB, not the DMB. Okay, because DMB is specifically for memory access, specific memory accesses, but DSB is a very strict barrier instruction. So you see that every processor completes everything before the new data is updated. So first, updating a translation table entry. So here in this case, we are changing the entry in a translation table. So translation table, we are changing one entry in the table, which is for mapping this virtual address to physical address. So I'm storing some data. So DSP ensures that the data is being modified correctly and completely in the translation table. Then after that, we are invalidating, means any data which is available in that particular address in the TLB is being removed, invalidated, and any branch predictions, it can be pipeline, everything can, it will be reflushed, pipeline will be flushed, and then DSB. DSB is ensuring that these cache operations and the branch predicted operations are complete before the processor goes and fetches the address or data from the new memory which is updated in the TLB buffer, translation Lucas site buffer. So you can see DSP is used here twice. So this DSP is used to ensure that the maintenance operations of the cache and the branch predictor is complete, so that processor can go and start execution or update data afresh from the whatever the address location, if it is instruction or if it is a data. Yeah. So this is a self-modifying code. Here P0 loads a new program to memory. So there are two processes, but like multiple also. Processor 0 loads a new program to the memory, which is then executed by both P0 and P1. So it is called a self-modifying code. So here also, because we're loading a new program to the memory, so first we are loading a whatever code into the memory. So memory can be data, or it can be flash, it can be RAM or flash. So here we are storing the data to the program memory. Then we are cleaning the data cache, because the same address memory, same address to which we are loading the new address of the PC, we are cleaning that the same address. So DSP will ensure that data is being written, and the whatever specific memory address to which we are loading the PC or whatever is being also ensured it is clean and it is empty. Next, we do the instruction cache. ICI is for instruction cache, and the branch predictor, again a DSP, to ensure that this instruction cache and the branch predictor operations or table, whatever it is been cleared. Okay. Then we set the flag 1 to signal the completion as to another processor, saying that the new program is loaded onto the memory and the other processor can easily start executing the code from the new program. Start fetching the address of the new program and executing. So ISB is because there is a context switch here again. So processor has to execute the code from the new memory, new address instead of the old address. So ISB has to be given to indicate it's a context synchronization event. Then we load the program counter to the address, which is again whatever the R1 to which we are loaded, the new program. Then program counter will load it to that and processor will start executing from the new code. So this is we are loading the code to the new program to the memory and we are signaling to the another processor saying that the new code is ready and it can execute. So DSP is very much required to ensure that address of the P1 is the new address is loaded correctly, modified correctly. Then we are after that we are setting a flag to tell to the other processor that yes, that a new program is updated in the memory. Next PC can be pointed to that memory and it can process and execute. Okay, so this is just to give a brief overview, understanding the barriers. See, barrier instruction itself is a very wide topic. It can be used in any scenario, but this webinar was to just get you introduced to what are the barrier instructions we have. Last time I did cover for the barrier instructions for Cortex-M, though it is not relevant there much, but this time I've covered the barrier instructions for the ARM architecture, specifically for Cortex-A and R. Okay, these are the main three instructions which you can use in your program based on the scenario and the requirement. So there's a lot of information available on the barrier instructions or the various scenarios. So we have this ARM architecture reference manuals. You go to infocenter.arm.com, which is now arm.com directly. So you can see that a lot of information on the memory barriers. Okay. Now coming to implementing this in C, we can directly use them as intrinsic functions, like DSP __ DSP function. So that will take it as an intrinsic function. Compiler understands that function as barrier and it executes, because barrier instructions are very much important. Okay. That brings in. And if there is any questions, I can take it up. So if there is no
Hi,
question,
Geeta. Can you go to the DMB example slide?
can you please put it on the chat? Please put your question on the chat. I'll answer it. Okay, DMB, I'll go. Yeah. So you can tell me now because we started talking.
Yeah, so if the instruction after the DMB one is add R0 #1, uh, so if the same register where the load was happening, so if it is being modified in the later instruction, means after DMB, so will DMB be sufficient or we'll need something else?
So in your case, you're telling add R2 instead of R2 if you're using R not only,
Yes, yes.
In that case, instead of DMB, DSP should do.
Okay.
DMB will ensure the load happens, but it cannot control processor to execute add output. Processor may execute or may not execute. But if at all processor executes speculatively, it can execute add R2, 1. Okay. So in
Okay.
if I put add R0, 1, then to ensure that the correct data is loaded onto the register R0 and then only addition happen, then DSP has to be used in place of DM.
Okay. Yeah.
Because data synchronization barrier is a very strict barrier instruction. Restrictive barrier instruction, to be more precise.
Okay. Yeah. Thanks.
So may I know who you're from? Can you introduce yourself?
My name is Devendra. I'm from Marvel.
Okay, Madhav. Oh, great. So any other questions? I know the topic is a bit dry, but it is very important. But hardly did not get participants for some reason. Um, right. So I'll just put down my mail ID. You have any doubt? So team, you cannot ask the question now, or you're busy. Please send mail to geeta@gsmspl.com. This is my mail ID. Any questions or clarification, or anyone is looking for license or some sort of technical support required, you can please reach out. Thank you, team. Thank you once again for making your time for this barrier instructions. It's a very good topic, though. We have to only understand where it has to be used. So the topic is very huge and vast enough.